Okay, in this lecture we're going to look at how to calculate work. So we'll be spending the entire section working on work. This is very applicable to physics, and a couple things I want to start off with is this table. So I'm not going to do a whole lot of unit conversions in this lecture. However, in physics, in the real world, maybe in your WebAssign problems, you'll have a lot of unit conversions. So if you're going from a smaller unit to a bigger unit, then that means you need to divide. Right? So if I have 12 inches and I want to go up to feet, I know there's 12 inches in a foot, so I need to divide by 12 to get 1 foot. Right? If I have 48 inches and I want to go to feet, I'm going to be dividing by 12. If you're going from a bigger unit to a smaller unit, then that means you need to multiply. Right? This means if I have 5 feet and I want to go to inches, I know there's 12 inches in a foot, so I'm going to multiply by 12 because I'm going from a bigger unit to a smaller unit. So I'd multiply 5 by 12 to get 60 inches. The other thing I'm going to mention is this table right here. When we're working in SI units, we will be working with newtons, meters, and joules. Okay? So the key thing here is that when we have newtons and meters, we get joules for our work. Now when we're working in US units, we're going to have pounds as our force, feet will be our distance, and then our work is given by this foot per pound. Right? So for this one, we're going to have pounds and feet. Right, and as promised, we've got some Florida Gator colors going on this lecture. Okay, so that's the important thing, right? When you get to a problem, you either need to put everything in terms of newtons and meters, or you need to put everything in terms of pounds and feet. Okay, this table will be very important for this section. So in physics, a force describes the push or pull on an object. We can calculate force by using force equals m times a, where m is the mass of our object, and a is the acceleration of the object. A lot of times this acceleration ends up being gravity, and we call this the force due to gravity. Okay, we can then calculate work performed on the object depending on the type of force being applied to the object and the distance the object moves. If you are being given weight, then you are being given the force due to gravity, right? Weight is equal to mass times gravity. Okay, let me write that down. Now, for whatever reason, the textbook is just entirely focused on using 9.8 meters per second squared as gravity. I'm used to saying 9.81, but we'll go with what the textbook wants to say, right? It's just how accurate do we need to be about our weights, which will affect our work and stuff like that, right? So we can also call, like I said, weight is the force due to gravity. So if you're being given a weight, you don't need to multiply by 9.8 after that. If our force is constant, then we can calculate work by using work is equal to force times distance. For example, here, I'm being asked how much work is done in raising a 60 kilogram barbell from the floor to a height of 2 meters. Okay, this kilograms, this is a mass. That means to get my force is going to be my mass, which is 60, times acceleration, which is gravity, which is 9.8. And then we will multiply by 2 to get our work, right? Because work whenever we have a constant force, meaning our force is not changing while we're moving the object, right? So while we're raising this barbell, it's not changing, right? The force is not changing. This thing still has a force of 60 times 9.8, no matter where it is in this 2 meters. So our work is going to be force times distance. So this is 60 times 9.8 times 2, which will give us 1176 or 1176. We have kilograms in meters, so this should be 1176 joules, denoted by that J. Now let's look at how much work is done in lifting a 50-pound weight from a height of 6 inches to a height of 18 inches. The first thing I'm going to do is notice that this is a weight, right? So this is my force. The force is just 50. There's no need to multiply by 9.8. To get work, I need my force times the distance the object is being moved. This is going to go from 6 inches to 18 inches. The first thing we need to do is notice that since we have pounds, this is going to be US units. So we need to put these inches in terms of feet. So 6 inches, if I want to convert that to feet, I'm going to a bigger unit. So I need to divide. So this is going to be 6 over 12 feet to 18 over 12 feet. Well, this is 0.5 to 1.5. And so the change in distance would be 1.5 minus 5, which is 1. So this is 50 foot-pounds for our work. Okay. Now, so these aren't too bad. When we have a constant force, it's pretty straightforward how to calculate the work, right? Find your force, which means if you have a mass, multiply by 9.8. If you don't have a mass, then you have a weight, which means you're already being given the force. And then find your distance. Okay, if our force isn't constant, then we're going to have a little bit more work to do to calculate work. Yes, that pun is intended. If our object is moving horizontally from x equals a to x equals b, right? So here in this problem, we moved from a to b like this. And we can describe the force at each x value with some function f of x, then we can calculate work by using an integral. So let's look at an example of this. When a particle is at distance x meters from the origin, a force of f of x equals 2x squared plus 1 newtons acts on the particle, right? That means if my particle is at some position, x, then I can plug that x into this function, and that tells me the force that's being acted on the particle at that moment. And this force is causing the particle to move horizontally along the x-axis. We want to know how much work is being done to move the object from 1 meter from the origin to 2 meters from the origin. So let's say we have this horizontal line. Here's the origin, 0. The particle is currently at 1 meter from the origin, and we want to move to 2 meters from the origin, right? So these are our bounds right here, this 1 and 2. So we're going to be integrating from 1 to 2 our force function, which should be 2x squared. So I have work equals the integral from 1 to 2, 2x squared plus 1 dx. And integrating this, you should get 17 over 3 joules. Now, Hooke's law is going to be the force F required to maintain a spring stretched x units beyond its natural length. Okay, sorry. Let me try saying this again. Hooke's law says that the force F required to maintain a spring stretched x units beyond its natural length, this force is going to be proportional to x. All this means is that our force is being given by some function f of x, which is always going to be equal to k times x. K doesn't change. K is just going to be some positive number, and it's going to be known as our spring constant. Okay, so let's look at this in a problem. A spring has a natural length of 1 meter. If a 25 Newton force is required to keep it stretched to a length of 3 meters, I'm going to stop right here. This is my force. I know that it has to be proportional to x, so I know that 25 is equal to k times x. Well, I also know what x is. X is given by how far it is stretched beyond its natural length. So if it has a natural length of 1 meter and it's being stretched to 3 meters, then that means we have a stretch of 2 meters, right? We're taking it from 1 meter of length to 3 meters of length, which means I've stretched it 2 meters. So this x is going to be equal to 2. Well, then that tells me that 25 over 2 is our spring constant. So now, if I want to know how much work is done in stretching the spring from 2 meters to 5 meters, what I'm going to do here is I'm going to use our integral to calculate work. But what this is going to be, this is not the integral from 2 to 5. We need to take into account the natural length of the spring. So this is going to be 2 minus the natural length, so 2 minus 1, to 5 minus the natural length, so 5 minus 1. Right, so here it's important that we subtract the natural length. Okay, so now what function are we integrating? Well, the function we're integrating is the function from Hooke's law, which is going to be k times x. But we know what k is. K is 25 over 2. So this is going to be 25 over 2 times x dx. So this is 25 over 2 times the integral from 1 to 4 of x dx, which will give us 6 over 5, which will give us 25 over 4 times 15. Now we're using newtons and meters, so this should be joules for our work. Okay. Moving on from here, we'll look at example 5. Example 5 says, suppose the work need, right? So this is where you know I'm a math major and not an English major. Needed to stretch a spring from its natural length to a length of 5 feet beyond its natural length is 30 foot-pounds. Okay, what's important here is we notice that they're talking about work. Okay? That means that the work is, we know it's equal to the integral from a to b, and this a and b is given by how far we're stretching, the interval of the spring, basically. So if we have a spring that looks like this, and it gets stretched, whatever amount, if I'm trying to calculate this, the work in this interval, then what I want is if this is some, let's say x1, x2, and I'm going to call this n for natural length, then my a would be equal to x1 minus n, and my b would be equal to x2 minus n. Okay. Another way to look at that is we're going from its natural length, right? So let's say it has a natural length of 3. Then this lower bound needs to be 3 minus its natural length. So 3 minus 3. So this is going to be 0. No matter what its natural length is, we're starting our calculation for work at its natural length. So this needs to be 0. And we're going 5 feet beyond its natural length. So again, let's assume that like its natural length is 3. Then we're going 5 feet beyond, which means this is going to be 8. So we'd have 8 minus the natural length, 3. So this would be 5, right? We could have also gotten that by just noting that it's 5 feet beyond the natural length, which means wherever it's at minus its natural length is going to be equal to 5. Okay. And then this should be equal to kx dx, because Hooke's law tells us that the force is proportional to how far it's being stretched. Or sorry, how far it's being stretched beyond its natural length. Okay. Now, we're told what this work is. We're told that this work is 30. So this means that 30 is equal to, remember, k is just some positive constant, so I can pull that out. The integral from 5 to 0 of x dx. Okay, so then that tells me that 30 is equal to, if we do this integral from 0 to 5 of x dx, we will get 25 over 2, right? Because we'll have x squared over 2. We'll plug in 5, we'll get 25 over 2. When we plug in 0, we'll get nothing. And so then what I want to do is I want to get k alone. The reason I want to get k alone is because I want to know what my f of x function is. Because what we're going to need to do is we're going to need to calculate the work done in stretching the spring from 3 feet beyond to 120 inches beyond. Okay. So looking at that, we should have, well, let's see, let's get k alone. That means I need to multiply by 2 over 25 on both sides. So that'll give us 60 over 25 equals k. Which means if I divide both of these by 5, we'll have 12 over 5 equals k. Okay, so now let's work on this first question. We want to know the work done, okay, in stretching the spring from 3 feet beyond its natural length to 120 inches beyond its natural length. Since this is in inches, I'm going to change it to feet. So I'm going from a smaller unit to a bigger unit, so I'll divide. I'll divide by 12 to get that this is just 10 feet. Okay, so this is going to be the integral from, let's see, we're 3 feet beyond the natural length to 10 feet beyond the natural length of k times x. Well, that's 12 over 5 times x dx. Okay, and then when you integrate this and calculate, this will give you 6 over 5 times 91 foot-pounds. Okay, then it says, how far beyond its natural length will a force of 60 pounds keep the spring stretched? To do this, all right, so let's call this number 2. This is this beautiful maroon color that everybody asked for. So we have a force of 60 pounds, and that has to be proportional to how far the spring is being stretched. Okay, well, that's going to be k times x. But we already know what k is. K is 12 over 5. So this is 60 equals 12 over 5 times x. So I'll multiply by the reciprocal on both sides. So I'll get 60 times 5 over 12 equals x. I know that 60 divided by 12 is 5, so then 5 times 5 will give us x. And this is how far it's being stretched. So our answer should be 25 feet. Alright. Now, let's look at this next set of questions. These are going to be called the water pumping problems. What we want to do here is we have some tank full of water or full of some amount of water, and we want to know how much work it takes to pump all of the water out of the tank. To do this, we are going to evaluate each slice of water in the tank, kind of like in the past when we did volumes of solids of revolution. We kind of evaluated slices of the solid and then added them all together by using our infinite sum, which turned into an integral. Well, here we're going to have the same idea. This V slice right here, this is the volume of some slice in the tank. Or really what we're calculating is the area of that slice, and then accounting for our variable for integration. This rho times g right here, rho is the density of water, or if we were using some other liquid, this would be the density of that liquid, and then g is gravity. When you multiply density and gravity together, what that gives you is this thing called weight density. So for work, we're going to have the area of this slice times weight density times the distance from where we're pumping the water out. If I'm pumping water just out of the top of the tank, then I just have to account for, okay, how far deep in the tank am I? And then what's the distance between that and the top of the tank? However, sometimes we'll have like a spout at the top of the tank. So we may need to add on some more distance to account for that thing, going 1 or 2 meters above the tank. Now, the key thing to remember here is that this is not the total work. This is just the work to move that one slice of water to the spout or pump that we are pumping out of. When we calculate the entire amount of work, that's going to look like W equals the integral from A to B. Now, the important thing here is that this interval A to B is the interval where the water lies, or where the water is. I don't want to accuse the water of lying. Okay? So this is going to be the integral from A to B of this thing we call V slice, which is the area of that slice, times weight density times D. Alright, so let's look at how we apply something like this. Alright. So we have a tank that is in the shape of a cylinder. So the first thing I'm going to do is draw the most beautiful cylinder you've ever seen. Yeah, that top circle actually wasn't too bad, but the bottom one's looking a little unique. I think that's the word for it. Okay, it's got a radius of 5 feet, and it has a height of 10 feet. So all I'm trying to do is just get a picture going so we can see what's going on. And I'm going to give us a little bit more room over here. So let's move this over to the side a little bit. Okay. Now, let's see, I've marked, how am I doing with my information? I got the radius is 5 feet, the height is 10 feet. The tank is 40% full of water. So I'm going to start using this kind of notation for where the water is, right? Now, if I imagine that this is kind of like, if I'm measuring from like 0 to 10, then where this would be sitting at, if it's 40% full, then this has to be at a height of 4. Because 0.4 times 10 will give us 4, right? And so that's that distance from here to the bottom. Now, we're also given a weight density right here. I'll talk about later what happens when we're not given any sort of weight density. And they ask us to find the work required to pump all of the water to the top of the tank, and then find the work required to pump the top 2 feet of the water to the top of the tank. So the first one we're going to look at is all of the water. First, I just want to note that rho times G is equal to 50. So let's look at all of the water. When we look at this scenario, let me move this over here so it maybe makes a little bit more sense. Okay, so what I need is work is going to be equal to the integral from A to B. So that's the interval where the water is. So that's from 0 to 4. And then we're going to have V slice. Okay, so let's look at what V slice is exactly. If I take a slice out of this cylinder, it's going to be a circle, right? This is that V slice. I'll just call it VS. Actually, I can write it out. Here we go. Whoop. So this is V slice. Now the area of this circle is going to be pi r squared. But remember, when you make a cylinder, you're just stacking the same circle on top of itself over and over again. So we know that this circle is going to have a radius of 5. So this is going to be pi, and I'm forgetting something. We need to account for what our variable of integration is here. So notice kind of if we put this into a XY plane. So I'm going to use a really good color real quick, yellow. That's a really nice color. Right, if this is our XY plane, then what I'm measuring everything with respect to is Y. Right, we're looking at everything up and down the y-axis. Okay. So we're going to need this dy, and this will be 25 pi dy. Okay. So V slice is 25 pi dy. Good. Rho, we already know, is 50. Rho times G is 50. Now this D. This D is the distance from where we're pumping the water out to wherever this slice is. This is why we're using a dy. This is why we're measuring everything with regards to the y-axis. Because we're taking some slice out of here, and I'm just going to say wherever this slice is, this slice has a height of y. Y units from the bottom, right? Where y is going to be somewhere between 0 and 4. Okay, so then the distance from this slice to the top of the tank, right? If I want this distance right here, this is 10 minus y. So our distance over here is going to be 10 minus y. All right, now we have our V slice, we have our rho times gravity, we have our distance, and so now we can calculate our integral. And when you calculate this out, you should get 40,000 pi. And so notice a lot of these integrals for these work problems are not like terribly difficult to calculate, right? Because this is a constant, this is a constant, this is a constant. You can pull all of those out, and then you're just integrating 10 minus y from 0 to 4. Okay, now what if we only wanted to do the top 2 feet of the water? Okay, so top 2 feet of water. Well, this is going to be, the only thing that's going to change here is our interval where the water lies, right? Now we're not looking at all of the water in the tank. If I'm looking at just the top 2 feet of the water in the tank, then I'm looking at the integral from 2 to 4, right? Here's our water in the tank right here. Or let me use the same color. Here's our water in the tank. If I want the top 2 feet, then I want to go from the top down 2. And so then that means my integral is from 2 to 4. If I had, say, 7 feet, if my water rose to a height of 7, and I wanted the top 2 feet of water in the tank, I would do the integral from 5 to 7. Okay, so this will be the integral from 2 to 4 of the exact same, I guess you can call it function. Times 50 times 10 minus y. Okay, and so then this should give you 17,500 pi foot-pounds. And a lot of things in physics aren't just like super easy for me to intuitively check, but what I do know is that it should be easier to move the top 2 feet than all of the water in the tank. So it makes sense to me that this number right here is going to be smaller than this number right here. And I need to put my units in. Okay, now we'll look at example 7. We have a triangular trough. Okay, so I'm going to attempt to draw a triangular trough. Okay, there's my triangular trough. It has a length of 5 feet. What this represents is that this line right here, this line right here, and this line right here, these are all 5 feet long. It has a distance of 2 feet across the top. So that means this distance right here and this distance right here, these are both 2 feet. And then it has a height of 3 feet. That tells me that this distance and this distance are both 3 feet. We're going to assume it's full of water. Okay, so I'm not going to draw a water level this time because it's completely full. Right, so that should tell us that already we know our integral is going from 0 to 3. Right, it's going from the bottom of the trough to the top. So we're looking at the height. Okay. Now we need to start looking at, well, I guess first we need to read the rest of the question, which tells us that there is a spout located at the top of the trough with a length of 0.5 feet. Okay, so I'm just going to draw this spout somewhere. There's my spout. This length right here is 0.5 feet. Okay. Now, our weight density of the water has not been given. When it's not given to you, it's safe to assume that it's going to be 62.5 pounds per foot cubed. Okay. Now, let's look at what a slice of this would look like. So a slice of this is going to look something like this. It should give us a rectangle. You can kind of think about the top of this trough as a rectangle. And as you take slices lower and lower, they're just smaller and smaller rectangles. Okay. Well, one thing I know for sure about this rectangle is that this distance right here isn't changing. This is always going to be the same as the length at the top of the trough. Okay, so that's always 5. What I'm going to do here is I'm going to go ahead and take this and kind of just pull it. Alright. So this is the rectangle that we have inside the trough. So I want to start labeling what we have. These are both 5. Right? What I don't know is I don't know the, what do I want to use? Well, let's use yellow. So that's a really nice color. I take it back. I don't want to use yellow anymore. I'll use purple. Alright. I'm going to call this the base of this rectangle. Now, let's take one of these triangles. So I want to show you what triangle I'm talking about. To do that, I'm going to mark this triangle with blue and blue, and then just draw it out to the side. Okay, so this is the same triangle that we're taking out of the tank. Okay, we know that this is 2. This is 3. Okay, we don't know what these blue edges are, but what we're looking for is this little red part that we have right here, right? Which corresponds to this and corresponds to this. I'm going to change it back. I want to know what that distance is. That way I can get the area of this slice. Okay. Well, I know that if we take, let's see. I need another color. Let's use purple. This right here is going to be like, how far up is this slice in our tank? Right? Are we taking the slice all the way at the top? Are we taking it at, 2 feet high, 1 foot high? Where are we taking this slice? So I just want to denote this by being y feet high. Now notice when we do our V slice, this should equal something with a dy, right? We need to have some variable that we're integrating about, which tells me what I want to do is I want to get b in terms of y. So this is going to be similar to this, right? And this distance right here is going to be y. I'm now choosing that realizing that choosing dark blue and purple is not the best choice. But notice that this triangle right here and our bigger triangle are similar triangles, which means that 2 over b, this proportion is going to be equal to, now let me show you where I'm getting these from. That's 2 from the maroon piece. B is the red piece in this triangle. This is going to be equal to 3, the overall height, over y, which is this small little height in our smaller triangle. I can rewrite this to say that 2y is equal to 3b. Now remember that our goal was to get b in terms of y. So now I can say that B is equal to 2y over 3. All right, so let me go ahead and replace that. So then our V slice is going to be 2y over 3 times 5. Which means that our work is going to be given by the integral from where the water lies, so that's 0 to 3, times, we need our dy, times our V slice, so that's 2y over 3, times 5 dy, times our weight density, that's 62.5, times our distance. Now remember, distance is the distance from our slice, right, the height of our slice inside the tank, to wherever we're pumping the water out of. So it needs to be, if we have a height of 3 for our tank, and then this goes up another 0.5, I know this isn't drawn to scale, then this total height is 3.5. So this should be 3.5 minus y will give us the distance from our slice, the vertical distance from our slice to where we're pumping the water out of. And when we integrate this and calculate, we should get 1406.25 foot-pounds. Okay, now we'll move on to look at example 8. In example 8, we have a spherical tank, right? So we have something that's going to look like, let's see, something like this, theoretically. Maybe I should make that like dashed. Now it looks more spherical. Okay, and in this sphere, we're told that we have a radius of 4 millimeters. So if I take this right here, let's say this is like the center of the inside of our sphere. That means like any distance, any point on the boundary, so like say here, 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 right? Any of those points, we have a distance of 4 meters to this point. So I'll just go ahead and mark this. This is going to be 4. All right. Now, we're also told that it is half full of a liquid that has a density of 900 kilograms, right? So if this has a density of 900 kilograms, then what I need to do is I need to, since this is a mass, right? This is a mass. I need to multiply that by 9.8 to get my weight density. So let's go ahead and mark down rho G. Our weight density is equal to 900 times 9.8. All right. Now, if this is half full, then I'm going to go ahead and draw a water line at this halfway full mark. All right, and I'm going to make this radius a little bit thicker. That way we can see it. Okay. Now, what we want to do is we want to find the work done in pumping all of this liquid through a 1 meter long spout, which is located at the top of the sphere. So I'll draw my spout up at the top of the sphere, and I'll know that this is going to be 1 meter. This is 1 meter long. Now what I can do is I can kind of represent this with like an XY axis. So if this is 0, well, the radius is 4, so this part would be 4, and this part would be 4. So in total, this is going to be 8. So this point up here, this would be 8. And then adding on 1 for the spout, this would be 9. All right. So Now what I want to do is take a slice. Alright, there's a slice of our sphere. This is our V slice. And we know that this is going to be equal to pi r squared. What we need to do is figure out what r is equal to. Right? We want to put this in terms of y. Sorry, this should be pi r squared dy. Alright, so if I do that, well, let's see. This right here, let's make this thicker. This is going to a boundary point. I cannot draw this. This is going to a boundary point, so this must have length 4. Okay. And then let's say that this slice is y units up from the bottom. Okay. Here's the center of this slice. And we're going to say that this is y units up from the bottom. Then this segment right here would have to be 4 minus y. Because remember that this entire thing is a radius, so that's equal to 4. And so if we have gone y units up from the bottom, then this little smaller piece right here is going to be 4 minus y. Okay. Now, what I want to do, I'm trying to make a triangle here. I'm not doing it very well. But now what I want to do is calculate this length right here. Okay. Well, this length right here is going to be the radius of our slice. Right? Remember, we said that this green point right here was the center of the circle of our slice. And so if we're going from the center of the circle of our slice to one of the points on this red curve, then this right here must be the r from this circle. Right, so I want to point out this is radius of red circle. Right? Which is the same thing as that radius right there. Well, now I've got a triangle I can work with, and our triangle looks something like this. Where these lengths are given by 4, 4 minus y, and r. So using the Pythagorean theorem, I can say that 4 squared is equal to 4 minus y squared plus r squared, which tells me that negative y squared plus 8y is equal to r squared. Right? We get that from FOILing this out and then moving it over to the left-hand side. So then that means that this is going to equal to pi times negative y squared plus 8y dy. Alright? So now let's go ahead and work on making our work formula. Pun intended. So this is going to be the integral from a to b. A to b is the interval where our water is lying. So our water is lying from 0 to 4. So let's see, we'll have v slice, which is pi negative y squared plus 8y dy. And again, it doesn't matter what order I write these down in. We have weight density, so that's times 900 times 9.8 times, then the last thing we need is our distance. This is going to be the distance from the slice to our spout where we're shooting the water out. So the top is 9, right? Remember the top of where the spout is going to be at 9. So then that means that the distance between the spout and the slice is going to be 9 minus y, right? that means that this distance right here is 9 minus y. Okay? And then when we integrate and calculate this, we'll get approximately 768,458,6.96. Right? And then if we remember, we are in kilograms and meters right now. And if we're in kilograms and meters, then that means that our unit is going to be joules. Now for our second to last page. Here we have a tank in the shape of a cone with a radius of 3 feet and a height of 8 feet. So here's my cone. Radius of 3 feet, height of 8 feet. Right? Assuming it's full of water, what's the expression that represents the work required to pump all of the water out of the tank? Alright, well if we take a slice, we should get a circle. Right, taking a slice of this cone, we should get a circle in that slice. If I say that this slice is y units up from the bottom, then what I need in order to calculate v slice is going to be pi r squared. So dy. So what I'm looking for is a way to represent this radius right here in terms of y. What I notice is I can create some similar triangles, right? I can treat this as one triangle, and then we can treat, let's see, this part as another triangle. So let's see what that looks like. One triangle will look like this. Our similar triangle will look like this. We know that this distance right here is given by r, so that means that the whole thing has to be 2r. And then we know that this distance right here is given by y. Now this one we know here, this is 3. So then the entire thing has to be 6. And we know that the height is equal to 8. So that tells me that 6 over 2r is equal to 8 over y. Multiplying across, this says that 6y, I'm going to do 6 divided by 2 first. 6 divided by 2 is 3, so we'll have 3y is equal to 8r, which tells me that 3y over 8 is equal to r. So v slice equals pi times 3y over 8 squared dy. We don't have any spouts, so we'll have that work is equal to the integral from, we also know that it's full of water, so we're going to go all the way from the bottom of the tank to the top, so that's 0 to 8. We'll have our weight density, which is 62.5. We'll have our distance, which is given by 8 minus y, right? That's the distance from the top of the tank to where our slice is. times v slice. So times pi 9y squared over 64 dy. And then calculating that out, that should give you approximately 9424.78 pounds per foot. Okay? Now, for example 10, we're going to change things up a little bit and start working on rope problems. All right? So, I'm going to try to rope you along as we work on these problems. I'm sorry, this has all been building on each other. So, we have a 100-foot long rope, which weighs 0.2 pounds per foot, and it hangs vertically from the top of a tall building. By tall, I mean it's at least 100 feet tall. And we want to find the work done in pulling the entire rope to the top of the building. So I'm going to set up a picture here. Right? Here I've marked 0 and 100 because this is 100 feet long. Okay? I'm also going to change this 0.2 right here to a fraction because I like working with fractions more than I do decimals. Okay? My force is going to be equal to, well, let's see. If we're y down, and this will be dy, our force should be 1/5 dy. Right? Then our work is going to be equal to force times distance. The reason I've gotten 1/5 dy right here and not the total weight of the rope is because I only want to look at one part, right? We're not instantaneously pulling the entire rope onto the top of the building like at one split moment. Over time, we're pulling more and more of the rope, right? Which means that our rope will get shorter and shorter, so the weight that we have to pull is lighter and lighter. A different way to think about that is think about if we've pulled all of this rope to the top of the building except for 1 foot, then the weight of what you have remaining to pull up is only 0.2 pounds, right? It's going to be something that's fairly easy to pull up. However, if you were the person that had to pull, when it's at 100 feet long off the side of the building, then you're pulling something that's 200 pounds. You're not pulling just that 0.2 pounds for that 1 foot. Okay? So our work should be force times distance. So this will be 1/5 dy, because that's our force, times y. Where y right here is maybe like the point that we're pulling. It's kind of like when we take our slice out of one of our solids. And so then the work is going to be equal to the integral from 0 to 100, 1/5 y dy. And this will be equal to 1,000 foot-pounds. Okay. Another way to think about this is that your force is going to be the weight per unit times dy, that's our variable of integration. And then work is going to be the force times y, right? The point at where we are at. And then we integrate from A to B, where A to B is the interval of the rope hanging off the building. Okay. Let's look at another problem. We have a 500-foot rope that weighs 3 pounds per foot, and it is being used to lift an 80-pound weight up the side of a building that is 625 feet tall. We want to find the work that is being done. The only thing that's important about this being 625 feet tall is the fact that we don't have like this weight sitting on the ground with maybe like a bunch of rope laying down there next to it, right? This is all hanging in midair. So what we're going to do is I want to look at the work to lift the rope and the work to lift the weight, and then we'll add them together to get the total work. So going with the classic Florida Gator colors, we'll have the work to lift the rope is going to be given by, well, let's see, our rope is going to be from 0 to 500, because it's 500 feet long, all hanging off the side of the building. And then we'll have our weight per unit, which is 3 pounds per foot, times y, wherever we're taking that slice out of, dy. And so this will be equal to 375,000 foot-pounds. Okay. Now we'll look at continuing with the Florida Gator colors. Work to lift the weight. Well, the work to lift the weight isn't too bad because this is a constant force, right? We have this weight, which is 80 pounds, and it doesn't change weight the entire time. Okay? It's not like the rope, where the rope will be changing, because once we have part of the rope at the top of the building, it's kind of like we take that weight off of what we had for the total weight of the rope. Right? What I'm trying to say here is that if we have a building and we have rope hanging off, right? In this case, we have 500 feet of rope that weighs 3 pounds per foot. So this is 1,500 pounds of rope that we have to pull up. Well, now if instead half of that rope is already at the top of the building, and now I only have, say, I only have 250 feet of rope. Well, now I'm only lifting 750 pounds worth of rope, right? So this is going to be a lot less work. However, with the weight, that doesn't happen. It's there the whole time. So we're going to have a constant force, which means we should have the work is equal to force times distance, where the force is going to be the weight of the weight. So we'll have 80 times the distance we have to pull it up. So 80 times 500, giving us 4,000 foot-pounds. 40,000 foot-pounds. And so then our total work is going to be 375,000 plus 40,000, giving us a grand total of 415,000 foot-pounds. Okay. Similarly, another way I could have done this to maybe make it a little bit faster is we could have done the integral from 0 to 500 of 3y plus 80 dy. This would have given us the same answer as breaking it into the two parts that we did. Now for our final example, example 12, we're going to have a 200-pound cable that is 100 feet long, and it's going to be hanging vertically from the top of a tall building, right? Meaning that this building's at least 100 feet tall. So what we need to do, since we know we're going to be calculating work, is we need to figure out our weight per unit. So if I do my weight divided by my length, this will tell me that my weight per unit is 200 feet per pound. Okay. Now to get our work, we're trying to find out how much work is done in pulling the first 10 feet of the cable to the top of the building. So if we imagine this is the top of our building, we go down, here's our cable. Let's say this is our cable. And so it's 100 feet long, so here's 100, here's 0. What I'm interested in is just the first 10 feet. Okay, so then my work is going to be the integral from 0 to 10, since we're only concerned about that portion of the rope, of our weight per unit times y dy, giving us 1900 feet pounds. Now, this is the moment where we need to stop and realize that we have not accounted for something. Okay? All I've accounted for was how much it takes me to pull this green portion to the top. I haven't accounted for this portion of the rope that's attached to it, so it's making it heavier this entire time. So what I need to do is add that work for that portion to what we were already doing. So what I want to picture is that this is just some weight that isn't changing. And we want to pull it up how long? 10 feet. So we have that work is going to be the part that we accounted for, right? The green part, 2y dy, plus now I'm going to do our other part that we just noted, right? To get the work of this, remember, this maroon part never gets to the top of the building, right? So this is going to be a constant force. And that constant force is going to be given by the weight of this portion of the rope. Well, the weight of this portion of the rope is going to be its length, 90, times the weight per unit. So 90 times 2 times the distance that we have to pull it, which is 10. Right? So remember, this is our length of rope. This is our weight per unit. And this is our distance pulled. Right. And this will give us a total of 1900 foot-pounds. All right. And then that will conclude our section 6.4 on work. And so great work for all of you who have stuck it out through the end of this week and through all of these great dry jokes. Please let me know if you have any questions or if there's anything I can do to improve your learning experience.